Here's a concept map that I've crafted as a way to represent and summarize the key concepts and their relationships to one another for this week's chapter. Though I've said so before, do keep in mind that this concept map does adhere to some basic principles for concept mapping design. That is, key concepts are placed in circles, or what I might call nodes. You may also choose to put in other kinds of information. You may choose to put in a formula, if you so wish. You may choose to put in an image if it should convey the concept clearly enough. Also keep in mind that two nodes may be connected to one another via a line segment with a propositional phrase on that line segment to describe the nature of the relationship between the two nodes. Note that the line segments have an arrow at one end to tell us how to read the relationship between the two concepts. Note that I've used bolder colors to signify key concepts, and I have also used larger text in those same nodes to indicate the same. Similar but lighter colors, branching off from those key nodes in my concept map, serve to define particular clusters of coherent concepts. This concept map picks up from an idea we discussed in our last concept mapping exercise, namely the normal curve. Normal curve is symmetrical. It's sometimes described as being a bell curve. It has particular characteristics. We already know from last week that the mean, the mode, the median are all the same in a normal curve, and it has a number of other properties. All normal curves conform to the same kind of standard relationships between the mean, the standard deviation, and the shape of that curve. And we can describe these relationships using what Caldwell refers to as the 1-2-3 rule. This is not exactly a formal rule that would be recognized by all teachers and writers of stats books, but in this case, it proves to be a useful idea. More specifically, the 1-2-3 rule says that when we go out one standard deviation in both directions from the mean of our frequency distribution, we find that 60% of the area underneath the curve falls between these 2 points. In the case of going out 2 standard deviations from the mean, we find that 95% of the area underneath the curve falls between these 2 points. And lastly, but not least, as you well know, if we go out 3 standard deviations in both directions from the mean, we'll discover that there is about 99% of the area underneath the curve. Note that these features apply to all normal curves, regardless of what they might represent. So in other words, you could have a distribution, or normal distribution, but it has a particular mean and a particular standard deviation. In any event, the characteristics as attributed to the 1-2-3 rule still apply. So if you have a distribution for height, if you have a distribution for weight, a distribution for IQ, assuming that IQ is a normal curve, and as well as height and weight, they will all follow those same characteristics as described by the 1-2-3 rule. There is a particular kind of normal curve, a special one, you might say, and this includes what is called the standard normal curve. And it can be very useful and productive when we are attempting to compare normal distributions representing different kind of phenomena. So, for example, we might be interested in the height of men and women. Each of these, you might imagine, represent different kinds of distributions. There might be different means, different standard deviations for both of those distributions, but they would be approximately normal, and so we can compare the two. As with all normal curves, the standard normal curve has some other features or characteristics, if you will. The standard normal curve has 50% of the area to the left of the mean, and similarly there's 50% of the area underneath the curve that falls to the right of the mean. The mean, the mode, the median are all identical to one another, and this accounts for the highest point in our normal standard curve. Here's one thing that makes it quite different from all other normal curves. The standard normal curve has a mean of 0 and a standard deviation of 1. It's important to recognize that this is a theoretical curve, and this theoretical curves have particular properties. But it's these relationships that allow us to make particular claims about other kinds of normal curves. Now, the 1, 2, 3 rule is a useful rule in terms of identifying the percentage of the area that falls underneath the curve that goes out a certain number of standard deviations from the mean. In particular, 1 standard deviation, 2 standard deviations, and 3 standard deviations. But what if we want to know how much of the area underneath the curve is present up to, say, a half a standard deviation, or from the mean to negative 1.3 standard deviations? We might need some help with this, and thankfully we do. We have what is referred to as a table of areas, and this table, in our textbook anyway, can be found at the back of the book in the appendix. Most textbooks will have a copy of this table or a similar kind of table, and if you're really in a bind, you can easily find a useful table on the internet. Please remember that not all tables are going to tell us the same thing. With this image that I have on my concept map, I can determine the percentage of the area underneath the curve up to a particular standard deviation that's greater than the mean. So I can calculate the area underneath the curve up to, say, 1 standard deviation or 2 standard deviations. Note in this case it's not going to be 68% or 95%. That number refers to the area underneath the curve between -1 standard deviations and +1 standard deviations. Or in the case of 90% of the area underneath the curve, it's between -2 and +2 standard deviations away from the mean. With the table that I have on my concept map background here, it gives us all of the area underneath the curve from -infinity up to some value, and in this representation it describes it as being z. Z tells us the number of standard deviations one is away from the mean. So yes, I might be interested in 1 standard deviation, 2 standard deviations or more in the positive direction away from the mean, or I might be interested in, say, 0.75 standard deviations greater than the mean, and so on and so forth. Well, here's where the table comes in very handily for determining those areas. Let's say I was interested in determining the area underneath the curve up to, in other words, to the left of a z-score of 0.45, or to put it differently, 0.45 of a standard deviation. While referring to the table, I would go down the left column until I reach 0.4. This is the 10th value. And then I would follow over until my eye reaches 0.05. And where the row and column intersect, I see the value of 0.6738. This tells us that, to convert it to a percentage, that 67.36% of the area underneath the curve falls under the curve up to 0.45. Let's do another one. Perhaps we can do this in our heads since we know enough information to do so, and then we can use the table to verify it. So let's look at a standard deviation of 1. Or, in this case, to use the language that we're already using, a z-score of 1. We already know from the 1, 2, 3 rule that if we go out 1 standard deviation in both directions from the mean, we have an area underneath the curve equal to 68%. Half of that then is about 34%. And looking at our graph, we could say that this is the area that falls between the mean of 0, because this is the standard normal curve, and that mean is given as 0, and going out 1 standard deviation, or a z-score of 1. So that much is worth 34%. We still have the area to the left of the mean of 0. And since we know that we're dealing with a normal curve, it's symmetrical, 50% of the area falls to the left of the mean, 50% falls to the right of mean. So we've got 50% to the left plus 34%. That gives us 84%. So if we go to our table, we go down the left and we can see where we arrive at z equals 1.0, and then we follow along until we have 1/100 of 0 there, so 0.00, come down, look at the point of intersection, and we see 0.8413 or 84%. We should not be surprised. We had enough information to determine this on our own, but the table should confer for us that our value is correct. So last but not least, let's take note that everything we've been talking about thus far pertains to the standard normal curve. You will seldom be working with a standard normal curve. Let's say you had a collection of data addressing the IQs of all the first-year students at your university. We can calculate the mean, we can also calculate the standard deviation. And let's say that the mean is equal to 100 and the standard deviation is equal to 15. So if a person has an IQ between 115 and 85, they fall within the 68% of the distribution of IQs for the first-year students at the university. Well, let's say I'm interested in knowing how far away from the mean an IQ of 122 is. Well, we have a nice little formula to calculate the number of standard deviations we might be away from the mean. So if our value is 122, in other words, our x value is 122, we know that the mean for the distribution is given as 100 and the standard deviation is equal to 15. We can plug those values into our formula and calculate the z value, which tells us how many standard deviations we are from the mean. And with this, we can then go back to our table and determine things like the percentile value for where an IQ of 122 falls. So that's it. That's it for my representation and reading of the concept map for this chapter on the normal curve.